Hello, my name is Don, and today I'm going to tell you about magnetism. Now, this is a prelude to a series that I'm going to do about gravity, and of course magnetism is not because of its simplicity, but because we know everything about it already. It's an attractive force which is akin to gravity, and I want to explain how I believe that it works. And to begin, I'm going to talk about the iron atom. Now, when I talk about iron in general, I'm making a magnet and stuff like that, then I'm really talking about mild steel, because cast iron, it's got a crystalline structure and it doesn't magnetize very well. So if I refer to iron, then you know that I'm not sort of talking about cast iron. I'm actually talking about mild steel. But let me begin with the actual iron atom. Now, if you want to go into your search engine and ask about the iron atom, and it tells you it's much the same as any other atom. It has a nucleus and it has an electron field. Now, in the electron field, there are 4 electrons, and they tell us that they spin in opposite directions. Now, if that's the case, then it could be that they're actually not negative electrons, as they assume they all are, but it could be that there's 2 positive neutrons and 2 negative electrons that do or do not spin. Now, the thing is that if you go into your computer and you ask, can you actually see an atom? Then they say, oh yes you can, and what it looks like a bit of Hessian. And where the weft and warp cross, there's a little black dot. And they're all equally spaced, and that's all the detail you can really see. You can see an atom, but you can't see its actual structure. You can't see the electrons and the electron cloud or anything. You couldn't see if the electrons were rotating or not. Now, when they talk about an atom, how it works, then what they do is they put a very thin sliver of material into an electron particle accelerator, and I would assume that they filter so the very thin stream of particles go through and they hit one atom within a little thin sheet of iron. And the way the bits actually come out of it and fly, then they're actually forced. I would like to make a little structure, an experiment perhaps. I would like you to consider that I had 4 little iron bars and I magnetized them. And I had made, on the ends of the bars, I made some frictionless bearings. Now, I put the bearings so that there was 2 on positive ends of the bars, and there was 2 on the other 2 bars with the bearings on the negative ends. And I would put a target on the open ends of the bars, and I would mount these bearings on a vertical axle and leave them sitting there in the Earth's magnetic field. And so, if the frictionless bearings were good enough, then the bars would align with the Earth's magnetic field. So you would have 4 targets that were diametrically opposed. 2 on one side and 2 on the other in the Earth's magnetic field. Now, because like poles don't attract each other, then they wouldn't sit exactly together. They would be slightly spaced apart. 2 facing to the north and 2 facing to the south. And so you nip down the a little way down the garden or whatever, and you get your rifle out and you shoot at the targets. Now, if you shoot the one on the right hand side, then it'll move in an anti-clockwise direction. If you shoot the one on the left hand side, it'll shoot in the opposite, in the clockwise direction. Now, that means that while they're spinning, which is what happens with a particle accelerator, it's hit by a projectile and it disappears around the one way, and they trace which way it goes, so they assume that it's spinning that way. But it needn't necessarily spin at all. It could have been stationary, as I say, in the case that I'm making, the Earth's magnetic field. Now I want you now to imagine that I'm making a magnet, and I have an iron bar and it's full of these little atoms with the electrons pointing, like I said, and you place a positive pole on the one end of the bar and you draw it from left to right. And as you pull it along, then I believe like attracts like, not the other way. And what happens is you would pull all the north poles, all the positive poles, in the one direction. Now, when they get to the end, because the negative poles are diametrically opposed, they would turn, click, the other way. So you would have a protrusion of a line, because they all line up after one another. Of one side would have a protrusion of positive poles, and the other side would have a protrusion of negative poles. Now, when that happens with nothing in between them, then I believe you reach a stage where you have critical mass. And when this happens, what happens is, because there's nothing between them, then the two lines would join together. So that actually it would go along and a circle and back again. So that at this end, you would have two open ends, and the other end you would have a rounded end where two join together. You would have a horseshoe magnet. Now, if you have horseshoe magnets, then you have something that you can work with. And so let us pretend now that we have 4 horseshoe magnets, and we attach them in pairs, a positive to a negative, a positive to a negative, plus to minus, and they form a circle, they form a circuit, join together, and we do exactly the same with the other two. Now what we have there is 4 magnets that are joined together, and the two pairs have no attraction for each other. Now, if I wanted to join those two together, then I could take one of my little bar magnets that I made before, and I could stick it on the wall of one pair, and I could join it to the wall of the other pair and join the two magnets together. Now, if the magnet I use to join them together is heated up, get a blow lamp and heat it up, and it gets red hot, it would cease to be a magnet and the two would not be joined anymore. Now, if instead of heating it up I was to give it a shock, if it's a temporary magnet, then it would no longer be a magnet and it would drop off. And so that is sort of demonstrating the actual properties of magnetism. So that when I have formed my magnet, like I said before, and you have the continuum, you have the line that comes up and it's a U shaped at one end and on the other, then if you were to put the two U's of the horseshoe together, they wouldn't stick. And if the field that they create protrudes out of the end of the magnet, then you would get this repulsion business. Now, the other way around, If you put a negative onto it, what would happen was you have an open-ended chain that's sticking on the U of the magnet, exactly the same as what it does with the horseshoe magnets that I made in the first place. Now, the other property about how to destroy magnetism is something that I'll bring to your attention later on. And another thing I'd like to draw your attention to is that when you're making a bar magnet, you can't make it that it's a magnet on the sides and not at the ends. It is the longest length of it is where the magnetism is. If you get a crane with a big electromagnet on it, and you try to pick up a large sheet of steel, then when you pick it up, it will dangle on one corner. You can't put it on the middle of the sheet and pick it up unless it's a specially designed magnet to do this. With an ordinary magnet, you try to pick it up and you will only pick it up by the corner, by the longest length of the sheet. And that's another thing I will draw your attention to too later on. And next time I will discuss how that works, how an atom is a magnet. But it's not formed with two ends. A magnet has got a positive inside and a negative outside. So it's different, and so I will explain the atom again. Bye for now.